Okay, good evening, everyone.
Good
Good evening.
evening.
Good
Yeah,
evening.
Good
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 evening.
evening,
evening. Okay,
sir.
okay, welcome
Good
back
evening,
to the
sir.
IE398. This is the seminar class for the PhD program in Industrial Engineering, Mapua University. And tonight, I have, and again, Dr. Vira
Again.
again for tonight. Okay, well, I think all of you are already familiar with him, but let me introduce him first. Okay, again, okay, Dr. Wira is currently a lecturer in the Department of Industrial Engineering, BINUS graduate program, BINUS University in Jakarta. Formerly a research, he was a research fellow at Monash University, Australia. He received his PhD in industrial management from National Taiwan University of Science and Technology in 2017, and his current research interest focuses on the development of algorithms for optimization and its application in logistics and transportations problems. And for this evening, okay, it will be a very challenging topic, especially for me. Basically, I'm from human factors, but looking from the title is so scary. I mean, Metaheuristics, and then another one is vehicle routing problem. Those two are, for me, well, it's another world of industrial engineering. So, so for all the PhD students, okay, let's how we say that enjoy. I would say like another side of the industrial engineering. Okay, so let's welcome Dr. Wira.
Okay, thank you, Dr. Yogi, for again the introduction. Yeah, I hope you will not get bored to meet with me. Uh, I mean, yeah, like Yogi said that this topic might be challenging for some of you that not familiar with operation research or optimization type of topics. However, it could also be very interesting if you like. Well, I would not say like if you try to look into it, but sometimes you need someone to push you to go to there, then you will interested on it. And like me, actually.
Who was that? Who was
Okay.
that? Who was that? I mean, during your PhD, you have to tell me who was that.
Well, the story behind this is like actually I'm not quite familiar as well with this topic at first, and somehow it's just happened like there is a scholarship opening. I try to apply. I don't know what is going on, and then soon as I accept it, then I just realized okay, this is a totally different new world for me. And that is the thing that happened to me, so that I arrive at this point. But I quite fortunate that I have a good advisor that very I think it's I don't want to say kind because it's like I have meeting every week, need to have every week present the paper that relate to this topic. But yeah, that kind of activities let me become what I am today. Yeah, including the opportunity to do postdoc in Australia. It is also because I think the process of hard work and the the willingness to learn new things, and it sometimes life will lead you to the good place if you try work on it. Well, okay,
Can I
that's
ask
what.
Dr. Vira,
Yeah. Okay.
why you choose the supply chain for your, I would say
uh,
that can I ask, because I,
okay.
yeah,
uh
it's
Supply
totally,
chain.
no,
Uh-huh.
I mean supply chain, but this supply chain is not the supply
Yeah,
chain in
okay.
undergraduate. I mean, supply chain in undergraduate is just not this high level, but this is going to be very high level.
Yeah, this is much related on how operation research actually applied in supply chain. So there will be a lot of mathematical formulations, mathematical modelings, optimization stuff, algorithms especially, because those type of problem is complex. And basically, like I said, that the point that make me interested on this topic actually, I realized it not at the beginning of the time that I study, but up until I study a lot of papers, see a lot of topics on it, and I see the how to say this topic is discussed a lot in the industry. Many people talk about supply chain, many people talk about logistics, but somehow this topic is cover a very large area. So there is a lot of opportunity to improve on, including including also people from human factors, people from ergonomics, people from business management, IT. Uh, they have their own perspective and contribution to supply chain. That's actually one of the things that make me really interested on the topic, because even though that the topic is very widely open, but you can still contribute based your specialty on it. So it's a good thing. Like one topic you can share with everybody. You can relate with many people using through just one topic. And more specifically, this one, vehicle routing problems and applied metaheuristics. But before that, let me share my screen first to have a little bit of context. Okay, the title, this one, Metaheuristics is kind of a algorithm that is very robust actually. So this algorithm is proposed to solve various type of optimization problems. It means that when you arrive on a problem that you need to decide among a lot of possible combination of solutions, and it is very difficult to solve in a traditional way using some things that we call exact solution approach. Actually, metaheuristics can be one of go tools that you can use. So it's like even now I mentioned one of the application in vehicle routing problems, but actually when you uh, see this solely as an algorithms, you can actually see that the application also you can see the application in many areas. For example, I see Yogi paper also have experience to use metaheuristics for I don't know, maybe optimize some kind of choice.
Yes,
Yeah, you
yes,
want
I
to
did
say
that.
something? Yeah, yeah,
Uh, yeah, so it's actually for the obviously optimizing the camouflage for the military. I would say that military uniform. So how to make it more to be like undetectable. So how we need to do like
ah,
some kind of optimization. Yeah. So some
yeah.
kind of optimization. At the beginning, I did the response surface, the exact method, but
Mm-hmm, mm-hmm.
there could be something that beyond that
Yeah.
but that available data. So I found it actually the better optimum is actually that using meta heuristic. But the you know what actually since I'm ergo people and those things are ergo is only have eyes but we don't know how to do it. So we only know how to do it but we don't have the tools or like the lag how to do it, then that time I begged to, to one OR. You know her of
Okay,
course.
okay.
I begged to one OR sister, older,
Yeah.
old sister, that actually that she was the one who did the programming, and then she told me like, oh, this one is easy. I can just just code it. So I just changed the parameter.
Okay.
I ran it by myself, but the one who coded that one is actually it was not myself. So
Okay.
so for ergo people, be good with OR people, okay? Because we did OR people.
Okay. Yeah. Yeah. There
Okay.
is one example that you can apply meta heuristic to different type of problems other than VRP scheduling problems or any type of problems that might looks like annoying for you because of their mathematical formulations. But yeah, other than that, well, even when I go to several conference, I see many application of meta-heuristic, including for product mix for the energy and what else? Uh, yeah, many things. Like for data science, you have a lot of algorithms to be used in data science, and that algorithms perhaps need several parameter tuning. Then you can use also meta heuristic to optimize even the parameter tuning. Yeah, that kind of stuff you can use meta heuristic for. But for this presentation, I will try to give to share my experience, because I have quite a number of paper published in this field, especially using meta-heuristic for the VRP. And perhaps that can give you ideas to, if you're interested in, you can use the, well, maybe the similar steps for your own optimization problems. Okay, I will skip the introduction part. Um, yeah, well, I see my senior here. Hello, Pak Agus. How are you? Yeah, he's my
Hello.
senior in ITS and lecturer also in University of Udayana. Welcome,
Oh,
Pak Agus.
welcome. Welcome, Pak Agus.
Hello. Yeah, welcome. Thank you. Thank you.
Okay, yeah. So yeah, I already we did the introduction uh, uh, this 2 weeks ago, so I will skip this one. So basically, what I'm going to discuss with you today, I separated into 4 parts. First, I will introduce the problem itself about VRP and basic stuff. You may or may not know these problems, but this is actually one of the famous, well-known problem in optimizations field. And then from that, we will move to the meta-heuristic part of it. So this, I will introduce the concept of meta-heuristics and how it somehow applied to the optimization problems. And then I will combine how to implement meta-heuristic in VRP type of problems. And I will show you several examples from the publication that I've been made in the past years during my PhD, during my postdoc, and one of the recent paper that just published in 2021. And also for the closure, I will give you some perspective of research opportunity that if you're interested, we may or can maybe collaborate to work on, because I think VRP, meta-heuristics is a good topic that can be still have many rooms to improve, especially for you if you are PhD students. I think it's how to say, this topic it will be still have many opportunity to work on in the following future. Okay, I will start with the basic first. VRP. What is VRP? Actually, this problem can be found in the practical case when you have a company or you will try to outsource the handling of delivery activities or similar logistics activity to like pick up products or deliver products. For example, a logistics company like DHL, FedEx, or e-commerce nowadays also provide extra service that they can also include last mile logistic delivery activities. And the basic is you will say like we can see like there in the problems there will be a number of customer location point that need to be visited. It can be, in practice, it can be 10 to even thousands of customers, And let's say the company will have a set of vehicles. It also depends on the size of the company. It can be tens to hundreds of trucks or different types of vehicles that need to be assigned to the customers that need to be visited, that represent by these dots. And the whole plan is to have a route for each vehicle so that it would uh, minimize sometimes the delivery or transportation costs, or can also be in terms of maximizing the efficiency. It means that you will need to finish the job as early as possible, or also sometimes consider how to fully utilize the capacity of vehicle that you have. And well, in practice, this can be a very difficult problem, especially when you consider the real case applications, such as real case application mean real case constraint or consideration. For example, if you consider the time windows, like the opening and closing for each customer, so you can only visit them at certain time in the days. And then there is consideration also about multi products, multi vehicle, and each vehicle maybe have different capacity, and split delivery, multi depot, and sometimes also traffic and road congestions. So in practice, you may, if you work on logistics company, they may provide you in the solution for this problem in terms of software. So you can just use it and then put the data and try to solve and get the numbers, and then that will be your routes. But sometimes the software itself, it's based on my experience working on a project with several logistics company. Sometimes it's not very flexible to address their problems, because you know that practical real case problem may have many constraints that maybe not be available in the software that provided by the software developers. So, but anyways, if you able to address this type of problems that happens in your companies effectively, yeah, there is a very beneficial, how to say, there is a potential benefit that the company can enjoy, such as reducing in terms of transportation costs, increased vehicle utilization, and increased customer satisfactions. Well, because of the practicality and the how to say, the complexity of the problems, these topics, the VRP itself, has gained much interest from both sides, which is the practitioner in the industry and academia. So this situation led the VRP become a very well-known and well-defined and popular combinatorial optimization problems. So I tried to take one of the recent survey regarding the application of meta-heuristic on VRP. Here I will show you there is a lot of class family of VRP, which is here start from the most popular one, like capacitated vehicle routing problems, or CVRP. And then when you include the time windows consideration, there is another model called VRP with time windows. And up until to the one that gain many popularity now, such as VRP that consider environmental impact on the roads they generated, that is called green VRP. And also like the one that consider outsourcing their logistics activities to other party, like using third party logistics, in which model the basic model is called open VRP. And also there is like a less known type of VRP. For example, it doesn't mean that less known mean that less complicated. It's sometimes even more complicated and more, how to say, need more how to more because of the growing of the complexity, you need to be more careful on addressing those constraints in the models. For example, dynamic VRP and truck and trailers, and also there is a class of VRP that is being studied, but maybe it's not as popular as the others that I mentioned earlier, or maybe it's also because the topic is just gain uh, interest in recent years. For example, like electric vehicle routing problems. So a VRP that consider the utilization of EV, electric vehicle. This is very new, and you can also explore it. And VRP with drones, for examples, or this is not really new, but maybe it more popular in the country like US or China or Australia, like VRP with crossdock, because there they have many application of crossdocks in their country, and so on. So basically, this is just the how to say, the basic models. If you read paper about VRP, you maybe find many more variants, including the one that combine capacited VRP with let's say the one that I did, open VRP, I combine with VRP with crossdock, become open VRP with crossdock. That is a new topic, something like that. But yeah, you can even sometimes random number put and combine, it's become a new topic. But I would not suggest that one, since one of the merit of introducing a new VRP type of variants is to consider that new variants should really have a real practice applicability. So you may see that you may see that it seems why people just like randomly generating, just put some alphabet and say no. I think actually it's not happen like that, because most of the I'm sorry, let me check again. Am I sound clear? It seems
Yes.
like there is a, yeah, okay.
Yes, it's clear.
Let
It's
me
clear.
continue. So basically there from start from how to say, it start from the earliest the introduction of this type of problems, it getting more and more attentions, because yeah, we have many different applications in each study case. So they may be considered to introduce a new type of variants of VRP. Okay, that is from the family of VRP. And I think I will start with the very basic definition of VRP, in which actually from academic perspective, this is a VRP may have a similar definition with TSP. So because why I need to mention VRP and TSP, because for a person that come from, let's say, computer science, or like undergraduate from information system, they may also learn this type of problems, which is combinatorial problems, but not the VRP type. So perhaps if we say TSP, it will be more familiar to the ear of the publics. Well, TSP itself, or traveling salesman problems, is a problem where you need to create shortest possible routes to first you will given a set of cities to be visited by a salesman, and then the task is to find the shortest possible routes that visit each city only once, and the salesman need to return to the original cities. And well, it may look simple, but actually solving these problems is very complex and challenging, especially when you consider the number of cities, like more than 20, because the combination of the solutions could be uh, millions, maybe more. And I will show you later about that one. Okay, and VRP itself is actually um, uh, extensions, we can say, or variants of TSP, when you consider there will be more than one salesman, or in this case, we usually consider it as vehicles to visit several cities, in which each city will have their demands to be served by the vehicles. And we also have consideration of like to consideration of vehicle capacity. So for each city that you visit, uh, in each route, the total demand could not be exceed those vehicle capacities. Okay, and in the perspective of optimizations, okay, uh, brace yourself. So this is the way we see it as an operation research perspective. We can formulate those considerations in a term of mathematical formulations, or mathematical optimization problems. So basically, all these mathematical formula uh, has meaning that is related to the problem. For example, the objective of the problem is to minimize the total cost of each routes. Okay, so here this objective has the exactly that meaning. So CIJ, for example, it means that the transportation cost, it can be in terms of this travel distance, or it can be in terms of traveling times. So when you have a decision variables that mentions, okay, Xij is the decision variables that how to say, that decide whether you will have a route from nodes I to nodes J. And then when you sum all the decision that have the routes, then you will have the total cost of the or of each vehicles. Okay, I may not going to explain all this one by one, because this can be easily read in the paper, or in the book that discuss about vehicle routing problem. But basically, all these constraint will define the considerations that being strict in the problem. Let's say like the vehicle capacity here, and to ensure all the nodes should only be visited once, and to make sure that your you can only use a set of vehicles that available, and this one for the like we call it subtour elimination constraint, something like that. Okay, well, that's for the basic of VRP models. And well, if you can formulate the problems into mathematical optimization formulations, you can then use mathematical programming approach to solve it. Actually, there is a lot of way to solve mathematical optimization problem, but somehow mathematical programming is one of the most popular and common way to solve mathematical optimization problems. And to use mathematical programming approach, um, there is a lot of software available to be used to solve that one. And I did a initial survey that may be useful for you if you want to try to how to say explore mathematical programmings, or this type of software we normally call as solver, or mathematical programming solver. For short, we call it solver. And okay, here you may be familiar with several solver. For example, Excel solvers is very common to be used in as a teaching tools in the class, because yeah, Excel is widely available, but it's a proprietary software. Means like actually it's we need to pay for using those software. Well, the Excel at least it actually it's not for free, right? And this is the type of software that I list, and I think uh, it's powerful, but somehow you need to pay some money to have the fully function of the software. And there is a free software available as well, but it somehow not gaining as much popularity with the proprietary softwares. In the perspective of academics, actually there is a list of very powerful software that you can explore if you are interested on math programming. And I normally use this software because I found it somehow it is very intuitive and easy to learn. And yeah, it's academics means here it's they provide you the fully function the full feature of the software for free, as long as you use it for academic purpose, for example teaching and learning, and research activities, something like that. Okay, let's move to the next part. Yeah, go back to the formulations. And these formulations can be, so for mathematical programming, actually the first step is you need to have the formulations. And then the second step, you need to translate those formulations based on the mathematical programming language that you are using. For example, I use ample that I mentioned earlier, and you can see that the ample approach is literally not literally, it's basically just try to translate all the syntax in the mathematical models that I showed earlier into the syntax that is used by the ample mathematical programming. For example, I showed it to you earlier the mathematical model for the objective functions. Okay, let me show you again to make it uh, to let you have more ideas. Okay, let's say here we have sum from I for all I element n, and then sum for j element n, Cij multiplied by Xij. Okay, and it's literally translated into like this in the ample model. Well, of course, you need to define what is Cij, what is Xij. But basically, it's just like the double sum. You translated sum I element n, j element n, I not equals to j, Cij multiplied by Xij. Yeah, as simple as that actually. But somehow, yeah, even for me, I need to like, yeah, first I need to have uh, I have what do we call this one? Shock when you see a lot of math formulations and then now a lot of math variables here, and then you need to pick it one by one and translate it one by one. But after you pass that phase and then you try to make up your mind and then try to uh, to see it again in a more calm situations, maybe with cup of coffee or cup of tea, depends on what you need. Then I think this how to say, this way is not that difficult. It's like the first time you see a statistical approach, when you don't know how to interpret the p-value, you will very stressed to see a lot of numbers there, right? But when you know just, okay, less than zero point 0.5 will be what, more than zero point 0.5 will be what, then it's already done, something like that. This is a similar situation that happen for many people, I think, that having first time experience solving mathematical model. So first, okay, if you like cannot handle it at the first time, it's okay. Calm yourself, go do your hobby, exercise, or anything that you like. Then after that, come back again, see again. Actually, it's not that difficult. Okay. Well, if it's still difficult, maybe you change topic.
Or chicks the
Okay.
field. Because
Yes.
I already drink coffee. I always check again. Try to put that on my brain, but my brain keep telling me like you
Throw
are
it
ergo,
away.
you are ergo. So my brain is keep telling me it's okay, Yogi, it's okay, you're ergo people, so it's fine. Okay.
Yeah, because
It's okay, sir. I hate OR since bachelor degree.
okay, Thanathorn.
But
but
Tanatorn,
you still
no,
doing it.
Tanatorn is actually his master degree is a supply chain. So right,
Okay. Okay.
yeah, right.
Okay,
Your
I
master
have
degree
a
is supply
topic for you
chain.
later.
Oh, don't worry. You know what? All of them will meet up with you next term. So
Okay.
it's the time when you can explain it slowly. So at the beginning now is the shocking period for all of them, and next term they will have to do this by themselves.
Yeah, yeah, yeah.
So
Yeah, it's a
This
good
one?
opportunity.
This one?
yeah, yes,
So
yes,
you
yes. Artvin Ong. You know what?
you
Yeah.
have
Okay.
about 2 months
Artvin Ong, get
to
ready.
get ready. Yeah.
Yeah, so in May, you will, I don't know, in May or June, Dean Yang, when will the fourth quarter starts? June, I think. May, the end of May. Yeah, I think it should be, yeah, Dean, when will be the,
Now it's fourth week, so 6 more weeks. 7 more weeks after.
so the end of May, I think, I don't know, June, I think, the beginning of, early June, I think.
Okay.
Yeah, when I
Okay.
check, 1, 2, 3, 4, 5, 6. Okay, early June, June 5th, Saturday. So it's the welcoming time for everybody. Don't worry, I will also join. let me let me
Okay.
try
Okay.
to see how far I can go. So June 5th, Dr. Weira.
Okay. Okay.
Okay.
Thank you.
So
Thank you. Thank you, Yogi.
don't worry, all of you. You will see. You will see Dr. Weira soon.
I didn't see Dr. Yang in this slide, but hello. Thank you for inviting me. Okay, let me continue. So, those are the first introduction for the VRP. Then, how do we solve it? I already mentioned one approach, which is mathematical programming. But basically, there are three approaches that you can use to solve VRP. They are exact solutions, heuristics approach, and meta-heuristic approach. What are those? Okay. Now let me introduce you one by one. First is exact solutions. It is a set of solutions that a set of solution of a set of methods, a set of approach that try to find optimal solution. So among all the solution for the VRP for that particular problems, they will give you the best solutions. That is what promised by exact solution approach. Okay, an example for this type of exact solution approach, like met programmings that I already mentioned earlier, or a more nasty way I said it, because it's called brute force approach. If you are from computer science, you will understood brute force. Actually try all the possibility, and then you find among all those possibility, find which one has the best, let's say, routes, which one has the minimum travel distance. Then this is the optimal solution, right? That is brute force approach. Or there is also something called branch and bounds. It is also exact solution approach, in which you may or may not know it actually it commonly embedded in the mathematical programming softwares. For example, the ample that I mentioned earlier, you may see it in the interface. Perhaps you only translate from mathematical model to its syntax, but behind those syntax, when you solve it, actually it's called an algorithms like branch and bound or branch and price and many exact solution approach. So, but exact solution approach has how to say this one, you cannot rely always on exact solution approach, because to find optimal solution for VRP type of problems is very difficult, especially when you consider the number of nodes, let's say more than 15 or more than 20. Why is it like that? Let me give you a perspective. Let's say if you want to, okay, let's TSP first, it's easier. For TSP, basically you can find all the possibility but of the city that going to be visited in terms of permutations number, right? Let's say you have 5 city. So the combinations of the solution, perhaps like visit city 1, city 2, 3, 4, 5, or 2 and then 1 and then 3 and then 4, 5, or uh, 1, 3, 2, 4, 5, something like that. Try all the permutations of those 5 numbers, then you find all the possibility, right? Okay, and even easier if you say that, okay, TSP, you fix the first number, you will reduce to only find 4 permutations. And let's say if the number of the combination was only 5 cities, so you can only check actually only 24 combinations. It's pretty small. But see, if you grow the number of the nodes become 20, so you need to find 19 factorial of combinations. It's about, I don't know, let me check my notes. 100, how to read this, 120 quintillions permutations. Imagine your software need to find all those combinations before you can solve it. I think yeah, it is near impossible to find all those combinations before you can select which one is the best solutions. So that's why it become one of the limitation of using exact solutions, is that if you want to solve we call this type of problem as an NP-hard problems, or a problems that that the complexity is grown alongside with the number or the size of the instance. For example, for TSP, the size of the instance is depend on how many nodes you are going to consider to be solved. And if you start small, maybe exact solution still possible to give you give you the best or the optimal solutions. But when the number is as you can see more than 20, it's impossible to give you a good even sometimes a good solution will not be found if you are using exact solutions. Okay, then researchers come up with the ideas of using somewhat we call approximation approach. It comes from the practical side of this problem actually. Like, well, I actually for the routing, I don't need the optimal sometimes. I just want to have a feasible route and I can sure that this route is good enough, then this can be the solution for the problems. And this type of solution is called approximation solution, in which it consists of two types of approximation approach. We call it heuristics and metaheuristics. A heuristics is a set of methods that can find you a fairly good solutions, and it's very fast in terms of computational time. This type of approach is suitable for to be used as an initial solutions. Like if you have big size of problem, you use this type of solutions. But the problem with heuristics is that it tends to trap in local optimal. Yeah, because like for example, there is an algorithm called nearest neighbor for TSP or VRP. It's both the same one. The heuristics works actually very simple. They just use a rules. For example, for nearest neighbor, the rules is to visit the nearest city from the last city that you visited. So it's easy, right, to be compute. Okay, see all the city. Let's say you have 20, you select one randomly, and then see all the 19 possibility of visiting other city, and then you choose the nearest one. It's very easy, but those approach may give you fairly good solutions, but somehow it's most often is very far from optimal solutions. Then there is a meta-heuristic solutions. Meta-heuristics is a term for a set of methods that promise you that it can find near optimal solutions, or sometimes optimal solutions within a reasonable computational time. So it gives you the power of finding a optimal solution like exact solutions, but in a more reasonable computational time. For example, let's say if if exact solution will not give you a result in 3 hours, heuristics maybe give you result in 1 minute, but the solution is not that good. But meta-heuristic can give you a solution maybe longer than heuristics, let's say 3 or 4 minutes, but it promise you better solutions compared to the heuristics. And perhaps it can be very close to the optimal solutions. However, the drawbacks for meta-heuristic is that even though you know that you are certain, you believe that this solution can give you better solutions, they will the approach cannot guarantee that this solution is optimal. So the problem is that sometimes because the number of possible solutions is so many, you cannot compare it to the exact solutions. You don't even know whether this solution is the best one or not. Okay, that's another problem that I will discuss later. Okay, that is the basic introductions why we need meta-heuristic to solve VRP. Well, again, meta-heuristics, the basic concept, I can say it like this. Meta-heuristics, well, it's used to solve computational optimization problems. So it can be treated as a black box process. So they don't need to know what is the input. They just need to know how do you calculate what kind of things you want to do, minimize or maximize. They don't care what type of problems you are going to solve, what type of optimization problem you want to solve. As long as you tell the framework, this is the way to calculate the objective, this is the constraint that you need to consider, they will give you with output, something like that. So we can call it a black box procedures. And it can also be reversed as master strategy or a guide to provide a better solutions that compared to heuristics, which is tend to trap in local optimals. So like you can use it, you can use initial solution from the heuristics and then you combine it with the meta heuristics to guide it into a better solutions. That also possible for meta heuristics. However, even though it often give you a good solutions, sometimes near optimals, and it's quite fast, but the methods cannot guarantee the optimality of the solution that you that the algorithm give to you. And yeah, the rest is like actually not all the problem you should solve using meta heuristics. Okay, this experience also I got from when I doing my postdocs in Australia, because my college is mostly from mathematical science background. So actually they don't really believe on meta heuristics. They said meta heuristic is like trial and error. You try or find a new one, something like that. But for some type of problems that give you a good result, and then it's enough for you, right? Like that. But for some type of problem, for example, a problem that actually can be solved using classical optimization approach like branch and bound, branch and cut, or in during my postdoc there is they most of my college using approach like Bender decompositions, Lagrange optimization, which I just learned. So they tend to, if you can solve it, find the optimal solution, you find it. But if not, then meta heuristic is the last resort that you can use, something like that. Okay, and since meta heuristic is often written in algorithms, and then it means that also if you want to be more to want to have more understanding about the approach, you may need to have ability to implement algorithm. For example, you need to do able to do programming, coding, something like that. Okay. Yeah. Now go to the story and classification, history and classification of meta heuristics. For meta heuristics, well, actually there are a lot of algorithms that talk about meta heuristics. I provide a list that I think this one list of several, I can say, quote unquote important, because they gain so many popularity, especially for solving VRP type of problems. But it doesn't mean that this list will provide all of the meta heuristics that are available there out there. Well, I try to provide or propose a category for this list based on what do we call this one? A category based on generation cohort. So I think no one done this one like this before. So if you are interested, I think we can make a meta heuristic review based on this.
Is it your figure,
Yes,
Dr.
yes.
Ira? Really?
Yeah, I made this one.
Actually, you get. Yeah, I really like it actually. Although like I only know perhaps only two or one. I know two.
Okay, later I will show you. There is a lot of, even some with fancy names, and yeah, some funny as well. Okay, so yeah, if you are interested, we can make a and this is a good one because
Perhaps we
it
can
is
submit a journal.
yeah.
Just a review, something like that.
Just
I
a
think we
review. Yeah,
can
there
submit a journal.
it
Yeah, a
the
review.
review journal also good idea because yeah, it can get a lot of citations. Okay, let me start.
Yes.
So I propose a generation cohort because it is easier to make sense and understood by many people because it is often used by public. So in the early stage of meta-heuristic developments, I say baby boomer and Gen X era, meta-heuristics, if, the term of meta-heuristic is even not well developed because I think the development of meta-heuristics is also correlated with the development of computing technology. In this case, I will say computer, because we need to apply the algorithm in the computers that may need a lot of complex computations, and in this era, maybe the computers computing power available is not for public like now what we have nowadays. In those area, even in the earlier area, we can still see meta heuristics that still available and become the foundations of the later and more sophisticated algorithms. For example, nowadays you can still hear algorithm called genetic algorithms. It's very popular and still being taught in the class because the sophisticated and very, how to say, insightful way of doing optimization approach. And actually the meta-heuristics approach, even the term is being used since the millennial era. I will say it like early 80s or mid 90s. I'm not sure whether the number here is correct, but somehow, yeah, it's in between that years when the computer start to be more well, everyone start to have their own PC. They can develop their own algorithms, and this is the, how to say, um, this is the era where meta heuristics gain popularity, and even some of the algorithms, meta heuristic algorithm introduced here, still considered as the best of meta heuristics to be used for some various a particular type of VRP variants, for example, like tabu search, simulated annealings, and several others. Okay, and then since mid 90s until now, we see a lot of meta heuristics being introduced, plethora of meta heuristics, I can say. Well, I think, yeah, because of the it is easy to implement. If you're already familiar with one, you can how to say, make sense of the other ones just based on the characteristics of the one that you already understood. And it comes with various fancy and even unique name. For example, well, the start is still quite okay and has a very beautiful concepts. For example, particle swarm optimizations and colony optimizations, differential evolution, variable neighborhood search (VNS), and getting to the recent implementation of the meta heuristic, I think there is more and more people or researchers adapt. I think we can say that natural wisdom from the nature, or swarm intelligence, and they can come up with like firefly algorithms, biogeography algorithms, cuckoo search, symbiotics or organism search, intelligent water drops. Yeah, the name is like, what is this? Something like that, right? But yeah, it, despite many criticism being addressed to those type of algorithms, several researchers, it still has many supporters actually, because even though they only provide a little bit of improvement, somehow some of them it still works and provide better solutions compared to the previous one that already available. And it can be used also to mix and match as a hybrid algorithms one with another. Okay, and well, basically we can, based on the meta heuristics that mentioned here, we can actually categorize it into two type of algorithms. The first one is something that we call single solution based algorithm, in which these algorithms will use single solutions at the beginning, and they will try to improve from those single solutions until the end of the iterations. And the other one is the one that have more popularity, is based on population base. It means that you will start with a number of solutions and you will try to mix and match between these solutions. Okay, so you will combine the characteristics of one solution with the another solutions that that is being used, that somehow called populations. Okay, and this population base, some review also categorize it into two type of algorithms. One called evolutionary computations, and the second one is the swarm intelligence that I mentioned earlier. Okay, and still it may have many more algorithms there, and many more maybe still under developments, somewhere under reviewed. So if you combine with those type of problems, of type of VRP problems earlier, and then combine with this meta heuristics algorithms, basically you have hundreds of algorithms that can be used to solve those problems. But if you out of ideas, yeah, you can use it.
Oh, I'm waiting actually, Wira search, something like that, So,
no, I will not
or
do that.
yeah, I'm waiting for your algorithm, Dr. Wira, or like what, meta heuristics, Mangsi heuristics. No, or like Wira-ristic, something like that.
Yeah, but
You can make your
the
own.
problem with this is actually like uh, I don't really like to do contribution.
It's okay, because later on that people will try your algorithm and then it's not that good and then you will be criticized, but the citation is getting high from the critics.
Cited because criticized.
Yeah, because criticized and so on.
Okay.
Anyway, Dr.
Yeah.
Wira, which one is actually
Okay.
from all of this one, for someone like me, when I applied at the beginning of that one, I only applied the PSO, the
Particle swarm
swarm.
optimization.
Actually,
Okay.
yeah, I only utilized particle swarm because that time that's the easiest one, the coding that I could understand. So I chose the particle swarm and I submitted and then from that one I did how I say that visual search using the I would say that with the subject, human subject, the experiment, and something like that. So that's the ergo part. But I tried to submit that one to the expert systems with applications. You know
Yes.
what? The comments. You know what? Actually, they say like, oh, this is beautiful,
Yes.
and then it's new thing, and then at the end reject. Like because it's the it's the method journal, because at the end
Yeah.
of the day, the two reviewers told me that it's beautiful, and then but this is the well written,
Yeah.
and then because ergo people always tell the story and then so on, and then but they told us this just like this is methods journals, so
Yeah.
I got rejected because of that one, and I submitted that one to the ergo journal and got accepted
Yeah.
very quite quick. So
Yeah.
how my question is which one should we learn first? Because
Okay.
at that time I had so many choices, because
Yeah.
like you can apply DE, okay,
Yeah.
differential evolution. You can apply I would say that and colony, for
Yes.
example, or you can
Okay.
apply a genetic algorithm for this case. But I was like, where should I
Yes.
start?
So many options. Yeah.
Yeah, so many options, and then I have to test that to the human, because
Yes.
that's my field. Yeah. So for me, it's the challenge. So how would you suggest to us to for someone who wants to start learning the meta heuristics? Yeah. So
for learning, actually, I guess there is no correct ways. I mean, like the best answer for this one, because everyone will have their own preference. But for me, what I can suggest is like it will be very fortunate if you have um, uh, let's say for your field, there is a research, previous research that also conduct metaheuristics. Why I say that? I will give you example from the field that I work on. But why I say that, because we call this part is doing literature review or literature research, right? So you will get some informations from that type of paper or research that mention, okay, I tried this algorithm already and this works, and I tried this one, it doesn't works. And you can see from their characteristics which one will be can be useful for your type of problems. So that would be my answer. For example, for my problems, I work on VRP, and I saw my professor already conduct a research on VRP, and he used simulated annealing, and it's quite successful. So I tried to use the same method, but different problems. And somehow, because advisor, they will give you advice, right? This is how to make it works, and then you have a better chance to apply it successfully, instead of just doing random pick and then try to apply it, and somehow the chance of make it works is less than compared to the one that already have a guideline from either previous researcher or or your partners that can help you, something like that. That would be my answer. So I can say PSO is good, I can say VNS is good. It depends.
Okay, because like
Okay.
I actually I worked with Dr. Farah at that time, and then
Okay.
I did not have any justifications, and then she told only by looking at the nature of the data, she just say like oh, this is PSO is good, see, I was like why is that good? It's just like well,
Yes.
experience. She told me like that. She told me like the experience, and then she applied. She applied the differential evolutions. That time like I said, D is bad, right? I'm like something like that. I'm like I couldn't get it. Why DE is bad? Why PSO is good? So basically that's that. Anyway, for those PhD who are specialized, who are specialized in human factors, for instance, like Yoshiki, doing metaheuristics in human factors, you will be published, very quick, really.
Wow.
Really,
Really, it combined
I'm like
two different areas.
No, not even two. Not, two different areas, but just a simple PSO. You know what? Just a simple PSO, and then it got accepted. I got accepted from the just simple PSO, because after that one, the difficult part is like I have to apply that to the. And not just the measuring the dot for me. I also have to test that dot to the human. Is it correct? Something like that, and it's correct actually. That applying the metaheuristics, abusing this the data mining, for instance, or metaheuristics in human factors. Okay. Or let me ask Artvin Ong, if you can apply these things, or for your concept, then I think it will be great. But of course, this is for the optimization, as long as there's an optimization
Yeah.
case.
Yes.
Yeah. If Dr. Weira could teach me.
Oh, I think not just teach. I think Dr. Weira can code it for us, and we just change the parameter, and then we get the result, and then test to the human. Usually, you know what? For me, I always make good friends, with so trust me that industrial engineering
Yeah.
is a
Yeah.
big field. You cannot master all of that, so be good
Yeah.
with the people from OR again. Because they are the one who can
Yeah.
help us, especially for the coding part. So basically,
Yeah.
anyway,
Yeah.
Dr.
Mhm.
Weira, another one.
Yeah.
I have a
Okay.
question from my. I'm
Okay.
actually quite curious with people from the OR field.
Yes.
Um,
Okay.
Actually, your publication is most
Yeah.
likely is the finding how's that the best finding a better solution for the similar case, or finding the
Yeah.
hybrid from here,
Yeah.
or
Okay.
I don't know the story in your
Yeah.
field,
Okay.
because I can see someone kind of like, wow, they're doing free hyper routing problem, but I don't know, it looks like
Yeah.
it looks like it's the same,
Yeah.
but they publish so
Yeah.
many with
Yes.
I don't know
I will
the in
show
your
you
field.
the example in detail. I pick very different example. Like I hope it will give you a good perspective for answering this one. I give you three different. I neatly pick three different example from my publications. All of those quite good journal, SCI, Q1, Scopus, and the first one actually choose simple algorithms. Choose a new type of algorithms. Try to combine it with several approach, but to solve the very well-known, well-defined problems. There is one
Okay.
like that.
Okay,
I will
so
show you later.
it's kind of
The
like
second
finding a
one,
better solution. Yeah, okay.
yeah, that one.
Yeah, that
There
one.
is
Finding better
another one.
solution, propose it. Okay.
Yeah, there is another one. I cannot find a better solutions, but somehow I work on the problems. I work on a variance of VRP problems that I mentioned earlier. You can combine several type of VRP problems. If you see in the real case implementations, these things is not yet been considered in the academics or in the paper. Then you can propose the new models. But I use
Something
only
like
simple algorithms.
new constraint like that, like you add
Yes,
like that. New
new
constraint, right?
constraint.
Oh, okay,
But
okay. So that's the
use
second
the
logic.
old
Okay.
algorithms.
Okay,
The
old
third one,
algorithms. Okay.
you have both new problems, new algorithms. Then you combine, voila, you can. Yeah, it's like mix and match, cook something new.
Okay, now I'm thinking like to continue my old PSO. I'm like because I
Just
know it's not
yeah.
yeah, it's not the optimum. It's just because meta-heuristic you cannot find the global optimum. It's just
Yes.
approaching the global
Yes,
optimum, and
exactly.
then it's random, Dr.
Yeah.
Weira. When I ran that one, sometimes it took me 4 hours to get
Yes,
the result,
yes.
and then
Mhm.
4 hours or like for me to really get the result, and then it's quite random. Sometimes it's up and down, and like
Yeah.
like
You need to improve.
so
You need to try to improve the we call it robustness of
the
the
robustness of
solution
the
generated by the PSO. Perhaps you can combine it with another
okay.
algorithms that can make it converge. The solutions can give you more like consistent result, something like that. Okay.
Actually, that my professor forced me to study about the OR that time, because like he told me like, hey, you are too cognitive ergonomics, you're really far. I mean, you always get out from something that is uncomfortable for you. And PhD, you know what? Sometimes you have to learn something that is uncomfortable for you to see it from, a bit, from different perspectives. So he forced me
Okay.
to
Okay.
study to study metaheuristics.
I think it's a good
And then
tools
like
to
that's
learn.
how. Uh, well, I only can understand PSO. The
Okay.
rest I cannot. I really for PSO I can understand for
Okay.
only for one, but that time. So I choose like, okay, okay for me to study only one because when at the beginning of that one, I'm kind of like nervous. It's like, oh my god, this is another world of
Mhm.
industrial engineering. And then but actually it's very quite successful for that one. But after the paper got published, I gave up because I graduated already. I mean, I graduated already, so I choose the thing that I like to do. So
Yes, yes.
but now I can see it's actually like applying this one in ergo is very big chance. Yeah.
Okay.
So
Yeah, I
yeah.
think so. Later, if we have students that can help us, because now the problem is not only what problem you want to do, what things you want to do, but how much time you have. Because you need to divide the time for this student for doing teaching and so on. So yeah, but it's a very good idea, Dr. Yogi. We can collaborate ergonomics using metaheuristics. It's a very,
Yeah.
very, very, very great idea, I think. Okay, let me
So
continue to show
yeah.
other students how I applied the metaheuristics algorithms for VRP. Okay, basically this can be these steps, maybe it will be different for your field, but somehow you can also how to say to I try to make these steps as general as possible, but somehow uh, if you want to apply this for any type of optimization problems, I think it still can work if you want to use this step as a guideline if you before you apply the meta-heuristic algorithms on it. Okay, first, because meta-heuristics is robust algorithms, it means that uh, any algorithms that you choose from that list that I provide earlier, they somehow have a robust characteristic, which means that you can adapt the 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 algorithms to solve various type of optimization problems. In particular, to solve a VRP problems, this five step of recommendation that I will suggest, which you could use as a guideline to work on your problems. Okay, first is to choose what type of VRP problem you are going to solve. Why I said like this, it's the same way why I answer Yogi questions with see what kind of problem you are working on. Because from the type of problems that you are working on, you will know the characteristics. Then you will see previous researchers whether they already implement meta-heuristic on it, and then to see whether your problem will fit with this type of meta-heuristics or not, something like that. For example, perhaps if your problems like there is one problems from construction engineering that I will that I take the algorithms to be used in the VRP. Later I will show you. The problems is a continuous type continuous decision variable optimization. So you will try to find a set of decision variables that is belong to a real number. So it can be integer, it can be a fraction number. And for this type of problems, I think one of the good approach normally will be algorithms such as PSO, and then and colony also good because they can work on continuous numbers. In by nature they develop the algorithms to solve an continuous type of problems. And the guy that I mentioned, the algorithm, the problem that I mentioned earlier about construction problem, they choose to develop a new variants of algorithms called SOS, symbiotic organism search. Well, it's actually very similar with PSO. It just has different formula and different how to say, different story behind the algorithms. Later I will show it to you, but somehow it works. It works, and the for VRP. After you see the type of problem you are going to solve, you need to understand what type of data you are going to work on. Whether you will compare it to the benchmark data set. If VRP normally several known variants, for example, CVRP, VRP TW, VRP with pickup and delivery, open VRP, it's already have a benchmark data set that many people have been tried many algorithms to get the best result for those benchmark data sets. And actually it's quite difficult to 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 compete with this in this type of how to say, this type of data sets. If you compare the solution, their solution may be already like near optimal, very close to optimal, something like that. So it's getting more and more difficult nowadays to compare with the benchmark data sets. Okay, and you can also, if your problems reflect the situation on the real case problems, you actually can generate your own data set. Okay, either you generate your own data set based on the parameter similar um, to the real case problems, or generate the parameter based on what you understood from several benchmark data sets. That's also possible for you to be, if you want to do that in the VRP type of research. And then after that, you need to select the solution representations. Well, what is solution representation? This is one of the important parts of doing metaheuristics. Well, metaheuristics, as I mentioned earlier, is black box optimization techniques. So they don't really care what problem you are going to solve. So if you want to use them, if you want to use the meta-heuristic algorithms, you need to tell them how you will represent your solutions. For example, there is a way of represent the solutions in a permutation base, like TSP or VRP, normally permutation based. Or you can also represent it in a binary form, like your decision variable, like for example, facility location problem. You want to open in that area or not? If open, the decision will be 1. If not, it will be 0. That's called binary decisions. Or you can have a continuous type of problems. Maybe like sometimes like parameter tunings. If the parameters between 0 to 1, what number you will choose? It can be any number from 0 to 1. That is a continuous optimization problems. Okay, and then after you select the solution representation, you also need to teach, or you need to implement in the meta-heuristic framework, how do you calculate the objective function from these solution representations, and then how do you handle the constraints. Okay, and after that you can choose what type of methods you want to use, a single solution base like SA, VNS, or tabu search, or any others like ILS, ALNS, and many options, or population based like GA, PSO, artificial bee colony, or SOS, the one that I will show you later on these examples. And for meta-heuristic, some meta-heuristic, you need to also do parameter settings. Okay, parameter settings, it means like, for example, how many iteration you want to use, you want to search the solutions. And then like for PSO, you may, it has like learning parameters, like you want to, how many you want to learn from the from your its own particle, how many percent you want to learn from the best of the pack in the the swarm, or the how many percent you want to learn from the past experience, something like that. That's also parameter. It's specific to the algorithms. You need to do parameter settings. And then the last, for VRP, you need to do benchmarking for the data set that you choose earlier. Okay, benchmarking means because you don't know whether your algorithm, how good is your algorithm, right? So you cannot also ensure the optimality of the solution generated by your meta heuristic. So you need to compare it with something else, whether it's the optimal solution generated by exact solutions or from the previous researcher that already conduct the same type of problems that you can work on. Okay, let me show you how do I implement those 5 steps. It's a good journal, but it's more specific to methods. They have many methods, including data mining methods, optimization method like meta-heuristics. You can find it in this journal. It's called Applied Soft Computing. It has quite a high impact factors and rank quite high in the Scopus. Okay, I think for this paper, for this journal, I submit several papers. I rejected so many times also. So it's normal if you try to submit to this type of journal and then you got rejected. But
How
somehow
many can I ask?
I think 3 or 4 times. I think I submit and rejected.
But you submit again.
Yeah,
You
no.
submit the paper again to this journal, Dr.
No,
Vira?
this one, I never submit to the same journal.
Oh, really?
Because,
We are quite different, okay? For me, if I think my work is good, then I will fight the reviewer. For me. And
yeah. It's different approach.
For my field, for my field, it's kind of like that. We can fight the reviewers, like when we think that it's something like not logical. But I think in your field, it's not like that.
Sometimes
So,
it's difficult. I mean, like to debate
sometimes difficult.
when they said like. Sometimes the rejection also cliche. For example, the contribution is not enough. How do you define not enough, and how do you define enough?
Like how do you define the contribution enough and not enough, right?
Yeah, sometimes it's like that.
Or sometimes like they say like, oh, it's not suitable for this journal. It's suitable. It's just you don't want to read something like that.
Yeah, yes. So that one is the unlucky part when you when your paper reviewed by someone that don't really understand what you're working on. They sometimes do use cliche rejection like that. But okay, for this paper, as you anyone want to ask question? No? Okay.
Anyone? SOS? SOS for what? Help? Help? I cannot I cannot take this anymore like that. SOS.
Well, this algorithm actually developed by one of our senior in NTUST. His name is Dodi Prayogo. He's a YouTuber now. You can search, quite popular, talk about stock market. SOS stands for Symbiotic Organism Search. Well, basically, it's a new algorithms at that time, 2012. I just used it in 2000. Actually, I used it 2014 or 2013, but somehow it kept pending, and just accepted in 2016. And I used the algorithms for problems that are already well defined, CVRP. So the challenge here is how do you justify that these algorithms is worth to be considered as a good algorithm to solve the problem, something like that. So since the basic algorithm is only uh, is designed for solving continuous optimization problems, so I need to borrow a concept of different type of solution representations. That one is another contribution from this paper. This solution representation, I show that it can help the algorithms to perform better to solve VRP problems. Okay, and the first step, second step, third step. The fourth step is the data that I use is a benchmark data set. So I compare with many algorithms or all known algorithms that already solve those benchmark data set. And I found it's a little, I think it's difficult because so many times I failed and try and fail again and try until I come up with this approach, the two solution approach, uh, which I also borrowed the concept from previous paper.
What is that
Okay.
one? Two solution representations. Yeah.
Two solution representations. They call it like this in the previous paper. It's actually specific solution representations to how to say, to represent the routes. So normally we just use permutation base 1, 2, 3, 4, 5, 6, something like that. For this one, they use a different types, which the vehicle is represented in coordinate x and y, and the routes is assigned to the nearby vehicles based on the random neighborhood generated, the new solution generated by the neighborhood. I will show you later the solution representation. Okay, this can be applied to any type of vehicle routing problems, but I'm not sure whether it can be applied to the other type of optimization approach. But how to say, later on, I also use this kind of approach to justify my contribution. So every time I have a new type of solution representations, I say that it's a new type of solution representation, something like that. So this is another way to justify your contribution in metaheuristics research. Okay, for VRP, it's simple. I don't have to explain again. Find a minimum total routing cost. Each vehicles, each customer only visited once by each vehicles, and the vehicle are constrained by the vehicle capacity and sometimes also maximum route length, or like maybe in the practice like time of the day, like 8 hours or 12 hours, depends on the company. And then okay, now the the SOS, the method itself, I will explain it in brief. So SOS actually it is claimed as a simple yet powerful metaheuristics. It inspired from the symbiotic interaction happen in the nature. So it's like in nature, yeah, organism is rarely live in isolation, right? So
Dr. Vera, this is the one that developed by Dr. Dodi, right?
Yes,
This is one.
Dodi Prayogo.
Dodi Prayogo, right? Oh, famous.
Yeah.
I remember.
Yeah, it's quite famous.
It's very famous. I think this. I remember someone told me the citations already 600 or something within.
Yes.
Within. I think he published it only a few years ago, and the citation is crazy.
2012. So, like I said, at
no, 2014.
This is
2014. I just checked it. 2014.
Okay,
and it's already 663 citations. Wow. So that's really a method person.
It is published at the right moment. So that time, not many people develop a new type of meta heuristics, and it's still considerably new to do something like this. And after that years, so many this time of meta heuristics being introduced, like you see earlier, many fancy names and actually not so much contribution. I will not say not so much contribution, but somehow it has too many similarities, just different stories, something like that. So but for this one, I think because I already tried at first, I also a little bit skeptic about this type of new algorithms, but as soon as I try it, the little difference here, like in the formula, like in the way you conduct the perform the neighborhood. We call neighborhood. Well, the term neighborhood is referred to how do you generate new solutions for your for your in your problem, something like that. The little difference there, here and there, makes somehow makes the results generated by this approach is somehow better than the previous the similar algorithm, for example PSO. Well, actually these algorithms is I think the story is like that. So you have in nature there is interactions. For example, in interaction that give positive feedbacks to both party interact, called mutualisms. I think we learned this one in biology, right? But somehow this story is can represent in the mathematical formulations by applying the movement that I think this is inspired by somewhat similar with the one that you see in PSO formula. Okay, the difference is just like when you say it's a mutualism's neighborhood, uh, it is actually try to improve both. If in PSO you can say it particle, you use this formula and then you check whether both party is improved or not. Okay, if both is improved, then you use it as the new solutions being used in the searching process. But if not, you take it out and go back to the previous solutions. So basically those are the main difference between these algorithms with the previous concepts like PSO. Okay, and then you have commensalism, in which you just try to improve one solution, one particle that being generated as a new solutions, but the other particle doesn't get any effect from the interactions. And then the last is parasitisms, is basically they the SOS frameworks see this as you try to like make the solutions quite different from the previous solution. So it's like introduce diversity in the solutions, something like that. So yeah, that's the main concept of SOS. It's pretty similar with PSO, but different implementations in terms of neighborhood, in terms of how they move to new solutions and how they accept new solutions. Okay. For the detailed implementation, I think I couldn't address it here, but maybe later, if I have time, I will try to make video or something like this for how to implement this one in, let's say, Python language or C#, Java language, programming language, something like that. But for now, at least I introduce you the basic concept. And then this one is another contributions that I said I did in the paper. So basically, common solution representation for PSO, it doesn't look like this, or SOS, it doesn't look like this. It will be consist of a real number. For example, if you have 5 nodes, so you will have like 0.1 and then 0.2 and then random for 0.3, 0.4, 0.3 and then 1.5, 0.15, and then you will sort this one become a route, something like that in the VRT. This is the common way to use convert continuous number to the VRP solution representations. But for this one, I borrowed the concept from I remember Professor Foratas from Thailand. He and his students come up with this concept for their PSO, and they saw that their PSO can perform much better when they implement this type of solution representations. It is basically it consists of 2 types of solution representation. The first one, they divide into 2 parts. First part is this is called the customer priority list. So the customer that you put in the front will be assigned first, and then it will be assigned, and then the later will be assigned to the later to the vehicle reference point in the second part of the solution representations. So it is somehow look like this part will consist of a pair that will represent the location of the solution representation point. And then from this solution representation point, you will take which customer is assigned to this vehicle. Okay, for example, okay, this one, let's say it's referred to this vehicle represent point. And then let's say customer, the first one assigned to this reference point is, let's say it's not 1 here, but 46. 46, so 46 will be assigned to the first vehicle, and then they will generate a route for the first vehicle here, like 46, and then let's say here 5, so go to 5, something like that. Then you translate these solution representations, and it will become the somewhat like the illustration that I show here. Well, it is done in the code that you develop, and this one is just the illustrations. And for the second one, it looked like this. It's somewhat similar, but yet a little bit different. The second solution representation, we use the first part as the solution vehicle representation point, which consists of pair of X and Y coordinates. And the second part we use to represent the radius of each vehicle. Okay, so when you have vehicle here, you will check how large is the radius in the second part of the solutions. And all the solutions all the nodes that belong to that radius will be assigned to the particular vehicles. Okay, and the rest that is not yet assigned will be assigned based on the nearest neighbor rules. And somehow the result of this approach, I compare it with the implementation of the PSO that also use the similar solution representation, and it shows that our SOS can somehow, I'm not sure whether actually it's not that much better here in the first data set, but it's better in the second data set. We have 2 data sets. The first data set, our solution is not much better, but this one is much better, something like that. And to publish this type of result, it's also tricky. I mean, like when your solution is not that good and you need to compare with so many solutions that have a good, very, very good result, this you need to, how to say, you need to really justify where your contribution is on the field of the study.
Okay.
Like
That one is actually you test the how is it that the vehicle routing problem with the several existing, your problem with several existing methods, and then if you actually if you would like to propose SOS on that one, so you show the result of SOS and compare with the previous metaheuristics like that. Is it like that?
Yes.
Okay, that's the case, right? Yeah.
So this is my proposed approach, and this others is the one that I particularly pinpoint on the PSO because its similarity, and then I also provide the comparison with others algorithm like SA, Tabu Search, VNS, everyone that have been solving these problems. I put them on the list and then I rank them based on the deviation to the best known solution. So
you know what, Dr. Wira, if this is your last one, if that is the result, you know what? For me, I have to test that to the human. So so you can imagine, right?
I mean like
for each for each you change the one parameter using one method, you have to test the result of that one to the human. So
that will be cumbersome. I think too many workload to do. Yes. But this one is done by previous researcher. So it means that I don't have to recode it again. So they already implemented. I just take their result and then I compare with what they found. Actually, my result is not that good here. As you can see, it's like in the middle of the pack. I don't know the rank of this algorithm right now, like in 2021, but in 2016, it's still like, it's not even in the top 10. But then that's the challenge. How do you say that this algorithm is good for CVRP? Okay,
then be politicians a little bit,
because you already do the research. It's be a waste of time. You don't publish it, right? So the way I did it is like, okay, this algorithm is similar to PSO. So among this algorithm, most of them is a single solution based. For population based like PSO that is more suitable for a continuous solution, a continuous type of problems, it is still considerably good. That's what I said in the paper. And then I use a statistical method to prove that this is not significant different and this is significant different. So that's one of the way you can do if you do this type of research.
Okay, so the new one in here is the SO.
Okay, this is SA for OVRPCD. Okay, this is I will just give you like a short explanation about this. It's like
simulated annealing, right? This one?
Simulated annealing. SA is for simulated annealing. OVRPCD, it's a new type of problems that I propose. So OVRPCD is combination of open vehicle routing problem with vehicle routing problem that consider in cross-dock situation. So you have open vehicle routing problem.
Can you explain that one by one? I mean, it's really out of my world. Sorry.
I will explain this one. Why do I come up with this new type of problems in the next slide? Well, this is basically pretty basic steps, right, that I mentioned to you earlier. And the main contribution here is how I propose a new type of problems because first, why do I propose this new type of problems, open vehicle routing problems with cross docks? Well, there is a already well-defined problems, so-called open vehicle routing problem. What is open vehicle routing problem? a common vehicle routing problem will have a closed loop in their routes, right? They start from depot and then we will be returned to the depot. But for open vehicle routing problems, the situation is different. You may or may not start from the depot. If you start from the depot, you don't have to return to the depot. But if you not, it means like you visit the depot only once. Okay, the situation happened in the real case when you outsource your logistics activity. For example, you hire the vehicle from outside party, from other company. So, okay, please do delivery for this customer, this customer, this customer, and this customer. Let's say 5 customer. So you pick the company that you hire to do the delivery will take the product from your warehouse, and then they will visit those 5 customer, and then they will not return to your depot because it's not your vehicles. It's belong to their vehicles. So the route will be somewhat called open route. Okay, this type of problem is already well defined. And then there is another type of problem called VRPCD, or vehicle routing problems with cross docking. Well, what is vehicle routing problem is with cross docking? First, you need to know what is cross docking facility. Cross docking facility is I will say an innovation strategy, or a type of warehouse that are not supposed to keep the product in the warehouse. Normally used to store a product, right, as a storage warehouse, right? But storage will store product in warehouse will raise the inventory cost, right? And there is many risks also involved if you keep your product in the warehouse, and you know that inventory is a waste. It means like you actually your company will be better, the efficiency will be better if you have less inventory. And warehouse is a concept where you will try as much as possible to not have inventory in the warehouse. So you call those facility as a cross dock facility. It is a famous, it has very famous applications and successful applications. For example, in the retail, such as Walmart, or those type of company could be beneficial from the implementation of cross-dock, because they actually need the facility to do the sorting from their suppliers, and then in a very short amount of time, and then mix and match which product will be delivered to their retailers. So Walmart sells so many things, right? They have many products from many suppliers. So their cross-dock facility is a facility that they can use to sort the product, label it, and then deliver it into the retailers that need the products. Okay, so and somehow in 2000, I think this one 2012 or 2013, this type of model is not yet available. So VRPCD normally will not. It's already been available. It's already being used in practice, but it's not yet available in the literature. It's not yet being modeled yet. So I try to come up with a new model for this one by combine those 2 available models in the basic VRP. And then you come up with this one. And this one
Okay.
is
So the new type is so in here. I know. Now I realize that I can catch up. So the new constraint is the contribution. Okay, I got it. And the SA is just the regular SA, right?
The SA is just regular SA.
Wait, let me
basically
check
I modified somewhere. I don't really remember as well.
Okay.
I will show you again the SA later. So basically this model we divide into two because it's crosstalk. You will need to have two independent variable for the pickup process and delivery process. And I don't really remember also which part I modified, but it somehow this type of model can accommodate all those considerations that is necessary for making it become OVRPCD. Okay, and then you can use the basic SA. Well, what is simulated annealing? Simulated annealing is also meta-heuristic algorithms, but it's different with the previous algorithms that I mentioned. This algorithm is a single solution base. So you start with a single solution and then try to improve from those solutions until the iteration is finished. However, it has a mechanisms like every other meta-heuristics. It will always have a mechanisms to escape local optimal or to somewhat we call explore bad solution. For example, the previous solutions, they will move based on that formula, whether it's better or it's not. For example, in the part, for the mutualism, it's not, it's always moved to better one, but for the commensalism and for the parasitism, they will not always go to the better solution. So that is the way they escape from the local optimal. And for SA, the way they escape from local optimal is that you allow the solutions that you generate in the earlier iterations to go to the worst solution or a bad solutions. But along the searchings, you will have a temperature parameters that will define how loose you will move to the worst solution. I mean, like for the early iterations, when you said the temperature is high, you will allow a very bad solutions to be explored. Okay, I go here, this is bad, it's okay, it's still early iterations. I try another one, it's also worse, it's okay, it's still early in the iterations. But along the iterations, you will reduce the probability to explore those worse solutions. Okay, so when the iterations almost at the end of the searching process, let's say if you have 100 iterations, almost when the iteration almost 90 or almost at the end of the searching, you will less and less allowed to move towards solutions. Okay, that is the concept of SA. Okay, so initializations, neighborhood is try the solutions, whether it's bad or not. You don't care here, but here you will have a rules, acceptance criteria. We call this one Boltzmann function here to decide whether you go or not go to the to use or not use the word solution. Okay. Okay, just like that. That's the basic concept. And again, it's an algorithm, so you need to implement it in the programming language or well, this is another problem with meta-heuristic is that I don't really see a framework that is very easy to use and implement like what we have in data mining. For example,
Yes.
data mining, we have Python framework.
Python
We
is
take
good,
the
yeah.
framework, many library, like like many library for implementing many data mining algorithms in Pythons or in R also available that you just need to put the data and then you choose what algorithms, then you get the results. It's not that there is a framework like that, but it's not that easy to use. So I think that's another problem with meta-heuristic. Okay, next, the third step is choose the solution representation. So I think one of the main point is that every implementation of meta-heuristic will have its own solution representations. There is a generic one. For example, this one actually a generic one when you have permutation-based solution representation. But I add several, we call this one dummy zeros. That is somehow I borrow the concept from the paper that published by my professor in NTUST. So this additional zero, it's simple, it's so small, but it can somehow help the solutions to get better results. Okay, instead of you are using only permutation based. And then the result, okay, again, there is for this one I compared with the old benchmark, which because I combine two type of problem, OVRP and VRP-CD. I choose to compare with VRP-CD because because actually it's easier. The OVRP part is difficult to compare with because so many people work on it. So for this one, I somehow can get a better result. Minus mean it's get better, better result compared to the previous one. They implemented using tabu search. Yes.
The instance 1 to 30 is the, how is it that you change the parameter, right? Am I correct? Instance 1 to
no.
What is that one?
Instance one. So they have three set of instance: 10, 30, and 50. 10 means there is 10 customer, maybe six in the pickup, 4 in the delivery, and we have 30 variety of instance like that. For example, there is maybe the instance 1 have 6 pickup, 4 delivery. Instance 2 maybe have 5 pickup, 5 delivery. So it's somehow simulate on several possibility of number of pickup and delivery in the cross-dock situation.
Okay, so that's the
Okay, so you have 30 instances, and then you compare it with those instances, and somehow these algorithms, it's simple algorithms, but it works quite good, and it can get a better result compared to previous benchmark instances. Then we confirm that we are confident to use it as an algorithms that we will use to solve OVRPCD. And actually this has a lot of criticism also from the reviewer, because for the OVRPCD part, we don't really compare it with another algorithm. We only compare it with the exact solution approach. And in this one, I use Cplex. So some solutions you can get zero means it is equal with the optimal solution. So you prove that your algorithm can find also the optimal solution as same as the Cplex. But for the bigger instances, the Cplex cannot solve the algorithms. Cannot solve the problem until optimality. So you get a better result. In this case, some reviewer may also ask you to do, okay, your result is better, but we don't know how much better it is from the optimal solution because you don't really provide the optimal solution. So in this case, sometimes the reviewer will ask you to compare with another meta-heuristics. So that happened for my other paper that I will show you later. Okay. Another one, okay, this one. This is I provide the improvement in both sides. The algorithms, adaptive neighborhood simulated annealing, and the problem. I extend from the previous model that I already developed for the VRPCD, but this time I disregard the open vehicle routing problem considerations. just use heterogeneous fleet vehicle routing problems and combine with VRPCD. Okay, and actually
Wow,
plus
there is
multi-input.
a Prof. Sao names there.
Oh yeah, Prof. Sao,
Prof. Sao, Prof. Sao. And for Thailand
our
students,
chairman.
Thai students, Parida Jepanya is actually from Thailand. She's from the, in the northern, near Chiang
Yeah,
Mai. Which university is that?
this one RMUTL, Raja
Rajamangala University
Manggala
of Technology.
University of Technology.
Okay, so Natakit, Ponyawat, and Tanator, you know what? I will invite Dr. Parida.
Yeah.
So during the, soon for the seminar, so you can say hi to her. She's very expert, like Dr. Wira. Exactly, she's very expert like Dr. Wira.
Yeah,
She is
yeah,
much
wait,
better
wait,
than
sir.
you. Okay.
Yeah, she is in a. I think I will. You know what, Dr. Wira? I think I will visit her after the pandemic.
Oh, great. Yeah.
I will, because I really want to go to Chiang Mai, and I think I
Chiang Mai.
will meet up with Dr. Parida.
Okay, great.
Okay, Dr. Wira, can we finish in 15
Yeah,
minutes?
it's already
My-
finished. It's like I will
My-
not explain in detail. It's just like new
Yeah.
methods and new algorithms,
Yeah, the
same
story. Yeah.
concepts.
My brain is
And
kind of like it's kind of
okay.
like, oh my god, this is
This is the last slide. This is the last slide.
Okay.
Okay. So
Okay.
basically, yeah, like you said, like you can see earlier, I show you there is a lot of variants of VRP problems. There is a lot of variants of meta-heuristic methods. But even though there is many people work on it, there is still a lot of research opportunity that we can do. So for you that interested on this type of problems and this type of methods, you can try to see or use this keyword as a guideline or as a hints maybe to where you can explore more in the future. For example, for VRP type of problem, dynamic VRP in which the real situation will be not like the one that I modeled earlier. It's all deterministic. You know everything in advance. But the real situation is like, okay, I create the routes right now, but in like 1 or 2 minutes there is new customer come. How will you deal with that? Or there is uncertainty involved. For example, traffic congestions, roads maintenance. How do you deal with that kind of type of problems in VRP? That's also one interesting topic. And environmental concern, of course, it will be, I think every type of research in industrial engineerings and management now try to, as much as possible, consider environmental concerns in their research. And specific to VRP, nowadays there is new last mile mechanism available. For example, sharing delivery or crowdsourcing delivery. That's also interesting area to be explored. Or a new type of delivery like drone delivery. That's also another importance, perhaps maybe become importance in the future. Electric vehicle, self-driving, deliver using robots. Okay, and for the methods itself, okay, in the future, I think since the computing power is getting more and more advanced and sophisticated, you can take a look like how you can combine the meta heuristic algorithms with exact solution approach. Okay, this type of combinations now is even already have the terminology called Metaheuristics. Okay, and there is also another yeah, this is like simple hybriding PSO and SA. Take the advantage characteristic from each algorithms, and then try to have a better result from those combinations. And don't forget that meta-heuristics can also be combined with several hot topics like artificial intelligence. So uh, there is a lot of research extension on this if you want to explore like combination of meta-heuristics and artificial intelligence. And hyper-heuristics actually it's not really new, but somehow it also has place in the term in the development of meta-heuristics. It is basically I can say combination between the use of simple heuristics as in it as a how to say as a neighborhood for the meta heuristics. Okay, well you can see in the paper later. In terms of technology, it is also interesting. For example, I also already mentioned that computing power is getting more and more powerful. I think up until now there is a lot of parallel applications in parallel computing because computing power rely on computing hardware such as either the CPU or the GPU. So parallel computing is take advantage of how many CPUs. Like for example, 8-core CPU. It means like you have actually 8 CPU embedded in your single hardware, something like that. And even more for the GPU, graphical unit computing. It has more core. It means like you can separate the process inside the meta-heuristic algorithms and make it work faster and better. And now I think this one, cloud computing is already available, like Amazon already provide you and Alibaba with Ali Cloud already also provide you frameworks to do the meta-heuristics in the cloud. So it will be more and more flexible. And I think this one for the future reference, perhaps when the quantum computing already set on, this algorithm will also move to that directions. Okay, I think I try to give I try to make it short, but somehow it's again
another 2.5 hours.
So, 2.5. I'm sorry,
Okay.
guys, but I hope
okay.
it's a good introduction.
Okay.
Yeah.
No, it's not introduction. I think it's already almost. No, it's like the what actually the people in your field are doing.
Yes.
Actually, that
Yes.
is. So basically, that this is another world of industrial engineering that you
Yeah.
know that. Now, actually, I want to learn. Okay, Dr. Vira, simple question. Okay, Dr. Vira, because I think all the PhD students kind of like shocked at this moment. They're like looking at because in here there are two things that they need to learn. They need to learn about meta-heuristics and they need to learn about the advanced constraint in the supply chain. So it's double burden. It's
yes.
Yeah, I know.
Exactly.
It's totally double burden at this point. So can I ask for your class, how will you for next term, for example, you like your class, okay? How will you strategize so all the students, including me, I will also join? But yes, I have experience with meta-heuristic, but only one. But learning meta-heuristic itself is already a new. Perhaps one term we cannot finish that one, but another one we have to add another the supply chain constraint. So I don't know whether in 3 months or
I don't think it's one. It can be delivered in one class because meta-heuristics normally is at one different class. And supply chain is normally one different class.
Another different class.
Another different class. And mathematical modeling as well is also sometimes
another different
delivered in. So I guess like we need to prioritize, like
Okay,
just
so
learn one,
do
maybe.
you have any ideas at this moment, when, because I think for this term is
Mm,
your
mhm,
last your last, I would say that session for this term in this
mhm, mhm,
class. So I think some
mhm,
students
mhm.
wants to ask like, how will you
Yes.
strategize for your
Mhm,
supply chain next year? Because now I can feel, I mean,
mhm,
for me myself, it's already
mhm.
a burden when the that part, because
Yeah.
I know how difficult that is to only learn the meta heuristic is difficult, and the
Yeah.
constraint in supply chain itself, it's another thing.
Yes.
So
Yes.
what would you strategize perhaps in the, but I
Okay.
think they also need to learn both, but how would you strategize your
Yeah.
class, Dr. Wira?
Yeah. I think I will focus more on the supply chain part of it. I mean, like my presentations that I delivered 2 weeks ago. I think, yeah, 2 weeks ago. It likes more on the supply chain part of it,
Oh,
which there I what I mentioned there, actually, like there is many way to solve problems in supply
yes,
chain, right?
yes,
So
yes.
I will give the how to say, I will lead the discussion to all of the students to see every part of the supply chain and try to come up. Every student can come up with any ideas or approach that they feel suitable for them at the moment to solve those problems. But of course, it should be done in analytical perspective. Like I mentioned earlier, there is a lot of analytical approach that you can use to solve the particular problems. Um, a good way to start, instead of uh, make it you have to do like this, something like that, because I also believe that there is a lot of way to solve a problems. So I will not really make my students, you should do meta heuristics or you should do mathematical modelings. You can come up with your solutions, but it should be a reasonable and data driven, methodological driven way to solve the problems.
Yeah, but
Okay,
usually
I
without
think that's
meta
it.
heuristics, I think the result is just, the result is just it's just not a PhD level, of course. Yeah, but I
Mhm,
think they can learn. I think they can continue at least three meta heuristics. You can continue your I would say that
mhm.
your model. I think you mentioned about the simulated annealing, SOS, and the PSO. I think
Yeah.
those three. I think those three is quite
Mm.
okay for the PhD students. How is that, student? Let me ask Artvin Ong. Are you ready? Artvin Ong. Let me ask some students.
This is this is very far from what supply chain and
I told you already. It's beyond
yeah.
expectations. It's what you know about supply chain is nothing
Mm,
really.
mm.
Perhaps this is the
Yeah, I mean,
level,
like,
the real
yeah.
level.
Like I mentioned earlier, supply chain is very
Yeah,
complex, very large topics,
but this is the high,
and
super very very high level.
one of them is this one, doing optimizations
Yeah.
using mathematical model, something like that. And I think if you it's a
Mm.
niche skills, actually. Not many people wants to learn this one, but I see there is a lot of opportunity available as well, if you somehow have the skills for this one. Okay.
Okay, Artvin Ong, are you ready for next term?
Maybe not meta.
Or let me ask Yoshiki Kurata. How is that, Yoshiki Kurata, next term?
Yes, sir. Sir,
Yeah.
um trying to be ready.
But anyway, this is the I would say that I think only few people in the Philippines, in industrial engineering doing in a very high level, abusing 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 metaheuristics in a supply chain like this one. But I think you know what, Yoshiki, at least you learned one or two. I think it will be useful. I've done once with metaheuristics in human factors, and it worked really well. Although that I feel like doing once is enough for me. So okay, let me ask Natakit. Natakit, are you ready? Natakit.
Let me think about it, sir.
Okay. No need to think because we will learn together. Okay. Sir Arfing Abela. How is that, sir?
I think I can do it.
Yes,
Great,
good.
great.
You have to say that. You think you can do it. Yes. Let's learn together and let's see how far we can absorb. Okay. It's okay, not 100%. It's okay because I know that some of you already set your main domain. Like some of you go to cognitive ergonomics, macroergonomics, some of you do the safety culture, some of you do the anything. Or like Tanatorn, you got the master in supply chain from Mahido, right? So how is that? Yeah, so it's easy, right, for you, Tanatorn?
My I'm good at lean manufacturing.
Okay.
That's another topic as well.
Yeah, that's another world of industrial engineering. Lean manufacturing is another world of industrial engineering. Okay.
Yes.
Okay, let me go with Ponyawat. Ponyawat, are you ready? Are you ready? Yes.
Ready, sir.
Okay. Don't worry, Dr. Wira will facilitate all of us because I know within 3 months that actually Dr. Wira, you know what? Even my class, they are actually still doing the paper. So even after 3 months from my class, they actually keep continuing the paper. I know in 3 months.
Great.
Yeah. So actually, like in 3 months, because I did not set any kind of like final exam. My final exam is actually I would like to see their progress in my ergo class. So it's up to them choose the macroergonomics or cognitive ergonomics or physical ergonomics. I keep checking their progress, even up till right now. I know in 3 months learning the hard skill of those things is already difficult. Yeah, it's so difficult. And if I force them to make a paper out of the 3 months, it's actually quite difficult. So I keep tracking the progress. So perhaps Dr. Wira, you can also do that. You can keep tracking the
Then
progress.
how do you give the grade?
Oh, I give the grade first. Yeah, I give the grade. I give the grade first. But anyway, that if they cannot make it because they cannot graduate without 2 SCI, right? I mean, and then that paper actually I'm preparing those for their SCI. One of the requirements. Perhaps they can make one paper. Yeah, perhaps they can make one SCI paper from your class, my class, Dean my class, Dr. Ferra's class. So they can have various STI in different fields. But I know they will die.
But I think I will also provide options if it is too difficult for you to do those mathematical approach.
But there are 3 things, right? There are 3, right? Usually, like whether you propose a new metaheuristics or whether you propose a new constraint or you propose both. So it's I don't know. I know I can.
Or you
get
can
it,
do also research literature review. That's also possible.
What about that, Dean? Dean Yang? Is it acceptable, Dean Yang? Literature review in financial engineering like that. Dean Yang? Dean, will you agree with that?
It's up to the professor what is his requirement.
Okay.
But if for example, in your class, the I say that the literature review in financial engineering, and it published in STI, you like.
It's possible, right?
Yeah, it's possible. It's possible.
Yeah.
It's actually pretty possible. Even in my field, I can do like literature review of what hand dexterity in the last 10 years. I can do it too. Like doing that without
it takes some effort, but to make it a really good literature review, I'm not sure whether like even me, I'm not really confident, even though I already published several papers in VRP, in Metaheuristics. I'm not confident enough to say that to because in literature review we understood the fields and then the future direction and how the researchers doing their research. So the literature review is normally for people that's already experienced on the fields. So that why I think that it's even difficult for PhD to do difficult literature review, because review that with that conduct by people that doesn't have experience normally not good. Yeah.
Okay, it's already late, everyone, and I know
Yes.
everybody for tomorrow morning they have the data mining class, so everybody will
Oh,
have
good luck.
and then I don't know. Tomorrow is still continuing the decision tree, perhaps, I don't know, or like for all the PhD students, including me. I'm learning data
Decision
mining
tree.
right now, actually.
Great,
Okay.
great.
For all the PhD students, any questions to Dr. Wira? Any questions?
Uh,
Sure.
I'm
Sorry,
actually
Doctor.
curious.
Yes.
Oh, curious of what?
Because Dr. Rira, I extended the study in supply chain. I'm not sure if you're familiar with um the author was Sarkar. This
I can't
so
really hear.
what? Oh, sorry.
You
Hello.
can, yeah. Yes. Okay,
Yeah.
you
Uh,
extend a paper related to supply chain. Okay. And then?
yeah. The author was Sarkar. Are you
Mm-hmm.
familiar?
No,
So oh
and then? And
he
what's the title
created
about?
a, a three-level supply chain
Okay.
considering um what's that? Lot size modeling, transportation,
Okay.
cost,
Okay.
and then
Mm,
his methodology was deterministic. He used an
yes.
algebraic base derivation.
Yes. Mm-hmm.
So,
Okay.
but that's the only thing that he did. He created a mathematical model of a
Yes.
three-level supply chain.
Yes.
So,
Yes.
if I would be extending
Mm-hmm.
that,
Mm-hmm.
incorporating something else, would that be fine also?
Yeah, for that type of research, actually there is this type of research, and like I mentioned earlier, for mathematical modeling, there is several options that you can use. For example, do the exacts method, including those mathematical programmings is one of the easiest one. That one perhaps is a little bit more difficult because you need to prove when you do they can say like, okay, if I derive this mathematical into this form, we can prove that we can find the optimal solution, somewhat like that. If I'm not mistaken, the lot size
Yes.
modeling and supply chain design, there is research related to supply chain like that. In Indonesia, the one that conduct research like that is Professor Nyoman. He has a lot of publication on that. I think for that type of research, there is a lot of things you can also do. But again, if you want to direct the result into like more complicated constraints so that it cannot be derived into some form that you can solve it until optimality, you can utilize metaheuristics algorithms. But if you somehow just want to I want to, okay, lot size, now it's static lot size, and then I want to make it dynamic lot size, that's also possible, but you need to have a very powerful mathematical background to do like proving the formulations, something like that. Okay, that's what I
Oh,
thought
okay.
about the problem. Yeah, I
Maybe
hope.
next time I can show you like
Yes,
in
sure.
class already.
Yes. Next
Yeah, but
term you
but
can
that's also
show.
a good topic. I mean, like that also well defined problem for a supply chain. So yeah, if you into it, just explore that one. I mean, like for the class, I will not push you should do this, should do that. But yeah, like you see, supply chain is very complex,
Very broad.
and
Yeah.
yeah, very broad, and then you can choose many topic there. Okay. Okay.
Okay,
Any
and then
Thank you,
others?
for
Dr.
Thank
the
you,
Rita.
okay.
Arvin. Mhm.
Okay, other questions from the Thai students? Any questions? Oh, I know the Thai students are very expert in coding because they.
Oh,
I heard
really?
in Mahidol
Okay.
is quite. Yeah, I heard in Mahidol is quite expert. Is that correct? The Natakit, Ponyawat, and the Tadator. Yeah, I heard in Mahidol is quite expert in that one. So let's see. Okay, next
Okay.
term you will see Dr. Wira. Okay. Okay.
Okay. Okay.
So